Perfect. Um, really appreciate that. Thank you for all of your patience for the slight delay in our start, but I promise that we'll still be able to finish by 11, and I'll not delay your next meeting. Great. So again, thank you very much for coming in for this tutorial. When I kind of signed on to take up this kind of tutorial talk, I was kind of debating what's the best way to kind of communicate some of the work that happens in my research group, but also kind of expand it to learnings that one could apply in their own research and in their own kind of ways of handling text data using large language models and generative AI approaches. So hopefully the key kind of learning objective from this tutorial is going to be for us to kind of learn from specific use cases of healthcare research, health services research that applies large language models, builds on large language models for a certain kind of specific task, and the task is computable phenotyping. So that's basically how I have kind of structured the focus of this talk. The title I have given, I know that we had a little bit of a broad title advertiser sent out. The narrowed version of it is kind of medical text data and training natural language processing systems using GenAI tools for healthcare research. Okay. My research interests are basically in these areas, but the way I kind of describe it, it is rooted in machine learning, which now in extended form is deep learning, in natural language processing, and in text and data mining. And through that, I build tools, I research on novel techniques to impact medical information extraction, consumer health informatics, clinical decision support systems, and trustworthiness of online data. When I say that I focus on these, it's really my team that does all the hard work. And what I'm going to talk about today is really fruits of their labor. So thank you all, the NLP for Health Research Group. In addition to research, I also teach in these areas. So my recurring course is a natural language processing course for health data that runs every winter term. And this is probably going to be the 8th iteration of it. And that's basically starting in January. So I know that some of the audience members here are graduate students who might be interested in this area. Some are advisors who could reach out to their students. This is a course that a lot of MIDAS enthusiasts, precision health certificate students, and MIDAS data science students take as an elective. I also have a series of 3 massively open online courses. One that's a long-running one as part of the applied data science with Python specialization focuses on applied text mining. There's one that is most relevant to this talk is a standalone MOOC on information extraction for health data. And then there is a similar MOOC that is getting developed, which is not going to be specific to health data, but more generally on information extraction using Python. That's going to launch as part of expanded kind of what we are calling the more applied data science specialization series. In addition, I usually take students for independent studies throughout the year, fall and winter term for credit, but also summer internships. So if you're interested, please do reach out. Okay, so you know a little bit about me. I'm going to take a little bit of time to know a little bit about you. And especially because we have about 35 additional kind of attendees. So if you can take a minute to chat, to type out what your kind of role is. Are you a student or a faculty member or an advisor or an external member? And maybe a little bit of where you are, your home location, that would be great. JJ, I see that you have raised your hand. Please, absolutely. If you can unmute and let me know, that's fine. Oh, okay. So there is a note that chat is disabled. Okay, thank you for that. We'll check that in a minute. It may be disabled, right? Yeah. Okay. 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 Great. So yeah, we are getting through that little bit of thing. Um, I can come back to it once that is set up. I can ask this question again. Um, but let me kind of move on. No, didn't do should not have done what I did. Give me a minute, please. Okay, yeah, that's correct. No, I can. No, if you want to go.
Okay, so for those of you online, if you have questions, please post them in the Q&A section of the webinar. This is a webinar, so unfortunately we can't re-enable chat, but please post them in the Q&A section when there are questions and we will answer them there. Thank you so much.
That's okay. Yes, thank you. So I should not have asked what I asked, but hopefully there will be a survey sent out at the end of the session, and please do kind of fill that survey out or feedback. But more importantly, kind of also share your kind of where you're coming from, because I do hope that we will be able to kind of cover most of it, and I want to kind of really understand whether it kind of matches your interests and so on too. So again, give me 1 minute here. Okay, perfect. Okay, great. So let's get started. And this first one is really more of an introduction. Give me 1 minute. This is okay. Something I need to pick up. Okay, good. So the main kind of point that kind of gets us motivated to this topic is that text data is really abundant in healthcare, but people don't really realize how abundant it is. There is a lot of clinical documentation that happens in day-to-day interactions between patients and their healthcare professionals. There is a lot of data that text conversation that happens in terms of messages that get sent between members of the care team, referrals, for example. There is patient portals from which patients can communicate directly with their care team, asking for questions such as prescription refills, but also certain additional kind of follow-up questions. And there is outside of the clinical documentation stream, a lot of text that gets generated when people are talking to one another in venues such as health discussion forums, social media, and the like. These data are difficult to search if you do not use a technique like search engines, an approach like search engines. There are search engine-like interfaces within the EHR system for the healthcare team. One of them is eMERGE, which is a tool that is housed in our Department of Learning Health Sciences, developed by Dr. David Hanover and his team. But outside of that, there is still kind of the messiness of finding the relevant documents in this stream of this massive health data. It's also tangled in language and the variation that language gives in all practical purposes for the healthcare system. Here, it's in English, but it could very well be multilingual, cross-lingual, and maybe even non-English if you're going outside of the US. And these data are complicated by the templates and the local dialects that are used. So it's very common to have acronyms that are or short phrases that the community or that clinic knows itself, but really not a standardized acronym that is used across health systems. So what does that look like is in terms of health data, it could come from really the true sources of health information, or high quality information that gets kind of compiled in books and journals and peer reviewed literature and so on. Just if you look at the peer reviewed literature here, as of basically this last week, my search kind of showed about 37 million citations that are indexed by PubMed. If you go beyond that into medical records, that is an order of magnitude higher. There are even from one institution, you'll see over 500 million documents which are there in Michigan medicine alone. And if you go elsewhere, if you can increase an order of magnitude higher there, and you'll see that in US alone in 2022, there were 6.7 billion retail prescriptions that were filled out. And these prescriptions are text again, because they are really talking about medication and directions for that medication. Take one tablet one time daily, and so on, and take with a lot of water and other instructions like that. So this idea or this area of work that takes in information from all of these places where text resides in published literature, EHRs, and prescriptions, and other places like social media related to health, and through those analyses, gain insights or knowledge that can help the healthcare improve. That is the core kind of fundamental need and functionality of medical natural language processing. The natural language processing is an area of AI, artificial intelligence, looking primarily on text, but integrating the information that is there in text with other information that one might find, for example, in the structured components of clinical documentation, for example, in a database with columns and information that is pulled out from forms and clearly kind of formatted. Okay. But then it's not a new technology. AI itself is not a new technology. Medical NLP has been in existence since 1970s and 80s. It has mirrored closely how these technologies have developed in general natural language processing itself, where primarily a lot of approaches early on in 1970s and until turn of the century were on expert systems, on rule-based systems that focused on decision trees and logical rules. Come 2000, the focus kind of changed on machine learning, where with statistical modeling to teach an algorithm to predict patterns, learn from these. And then even as early as kind of 2010s, there were talk about deep learning models. Early stages early on, but getting more and more sophisticated and complex neural network models that had access to GPUs in probably the late 10s. Come 2010 to 2020, and recently in the last 6 years, the focus, as you all probably know already, and that is the interest in this talk, is on transformers, generative AI approaches, large language models that are specialized deep learning tools that came from vision processing, for example, but then became kind of more and more specialized for natural language processing. And now in the generative AI realm, it is all of the above. It is not only text, but also images, and images working with text and audio working together. So when I am, so that is kind of the history of this, and we are going to kind of focus on technology in a bit. But let's look at what is the application area I have chosen for this session today. That deals with computable phenotyping. Phenotypes are characteristics for a patient or a group of patients that all have the same kind of criteria that can be useful for filtering or for identifying patients with those characteristics. And that comes typically from a combination of some sort of clinical work that has happened on them. So for example, somebody has diagnosed them with signs and symptoms, or diagnostic codes such as ICD and CPT codes, which are billing codes but associated with diagnostics. medications that have been prescribed and filled, labs that were kind of that have measured some value, some biometric, and included. And all of these are signals. All of these are individual components that go into creating this phenotype. An example of a phenotype would be, based on all of this, who has who is identified as somebody with Alzheimer's disease or other dementias, or who has a high risk of alcohol consumption and alcohol-related complications. So this computable phenotyping is a process of applying these computer executable algorithms to clinical data to derive cohorts of interest of patients with or without a particular disease, characteristic, or phenotype. And the ability to be able to do that at scale with high confidence is a challenge that that computable phenotyping with natural language processing kind of poses. So specifically, if you're looking at one task of cohort identification, your goal is to use these narrative medical records to identify patients who can meet certain selection criteria. For example, if you are part of a clinical trial and if you want patients to be part of a clinical trial and you want to identify them at scale, you would use some sort of cohort identification techniques or computable phenotyping technique to identify these patients. But when I say you have to get it from a narrative medical record, this is what it looks like. It looks like pages and pages and pages, and this is actually only half of what a note typically looks like of information. All of this, by the way, is de-identified. You'll see that dates are all kind of shifted and so on. Names are removed as well. But in general, then you would not you'd have them as sensitive information, right? But from all of this data and more, you need to find out one little bit of information that, for example, this patient is a male and that they drink two glasses of wine nightly. With this two information and the fact that there are certain characteristics that, let's say, the alcohol association kind of comes up, you can kind of infer that this particular patient is at low risk of alcohol use, because for males, 14 drinks a week or 2 drinks a night is considered under the threshold. 15 or more is considered over the threshold. For females, that number is lower. If it is 7 or more in a week, that is 1 glass per night, is considered under the limit, but 8 or more is considered over. So that is version 1. You are getting information from different parts of the clinical note or documentation or medical record, and then inferring a particular characteristic that can then be used for downstream tasks. You could also have another example like hypertension. In this particular case, this is clearly written out that this patient has past medical history of hypertension. You need to understand the structure of the template in which it is written out, in that it's a past medical history. Doesn't mean it has gone away. It's just that it has been there. And from that, infer that this person is positive for hypertension. So these are the kinds of characteristics that you want to pull out from clinical notes. How would you do it? There comes our friend of today, generative AI and natural language processing. And I'm going to talk about in these kind of hour and a half, really 2 use cases of them. One is a risky alcohol use case, where you need to identify patients who have high risk of alcohol use or high risky behavior of alcohol use. And Alzheimer's disease and related dementias, where you're identifying patients with Alzheimer's disease or Alzheimer's disease related dementias. But before we go into either of the 2, I want to focus on a tutorial of sorts on large language models. This is just to kind of level set, kind of depending on kind of the background that you're coming from, and my own kind of summary of really how the technologies have evolved over the last few years that has led us to today, that can then be used for these downstream tasks. So specifically, this part is derived from a lot of kind of talks, but most of the slides are coming from Dr. Kevin at Vanderbilt, his recent talk. Okay, so first and foremost, let's kind of see what is a language model. This would be a slight repeat for many of them, but it's still useful for us to kind of think about large language models in really what it can do or why it can do something significantly better than what language models can do, which has been in existence since 1990s or earlier. Okay, so language model is very commonly used in information retrieval. It is there in our Googles and Yahoos and Alta Vistas and Bings. Um, and it is a probabilistic model that, given a sequence of words, predicts the next word. Okay, so or identifies what's the probability of a word given this distribution. So if you have a string like this, Mira Paul met Dr. Jones at Mayo, what? For those who have health background and know about institutions, would actually kind of fill it in with clinic, right? If you all were in this room, I would not have given you the answer. If your chat was enabled, I would have asked you to write the answer, but I'm assuming that you all agree that that is what it would have been. Why do you know it? Why can you be so certain that that is how it's going to get filled with? Where have you seen this before? So where you have seen this before, as I said, is we have used this in information retrieval for many, many years. When you type in a Google search query and there is a next autofill or autocomplete, that is coming from a language model. When you are typing out an email and it tells you what the next phrase should be, that you can just press the space bar and kind of fills up for you, that is coming from a language model. So this is not new technology, right? So how do you predict what is the likely next word? Well, you look at lots and lots of data. You look at all of the data you can get your hands on. So Google decided that it's going to use all of the data that it has crawled and it has that available because it does an excellent job searching, right? To come up with word models. So if you were building a model that was just a single word model that just looks at the previous word, the question would be, what word would follow Mayo most often? So now if I say it this way, what do you think is the word that follows Mayo? It is things like mayo recipes or mayonnaise as a full form, right? Or mayo sandwich. Yes, Mayo Clinic comes in too. There are other arcane kind of uses, Mayo Bowl, that I didn't know existed, but that's also one. So you'll see that when you have a single word model, it is not giving, it is giving the most likely next word without kind of considering any other context. But we can do better. So when we look at this whole context, mayo recipe doesn't make sense or mayo sandwich doesn't make sense because it doesn't make sense to meet somebody at a mayo sandwich, right? So the context of even this one additional word at coming before has changed the probability of what the next word would be. So in phrases or sentences like this, what follows mayo, there the probability of cleaning then becomes more likely. So that is this learning these probabilities given that of finding the next word based on context. If you only used one word, that's the previous word, that's called a unigram model. If you use last 2 or 3 words, it's a bigram or a trigram model, which already is more complex than the unigram model. And your distribution becomes much more kind of, uh, it converges quickly to probably what the right word would be. So context of even 2 words is good. But you can extend that to n words, and that will be an n-gram distribution model or n-gram language model, or it could be the whole collection, and it need not be the last word or the next word. You can have what should follow this if you look at words following that word, and then infer that using the context window. So in kind of mathematical terminology, you're just finding out probability of the next word given the previous word. So probability of W word n plus 1 given word n, or last 2 words, word n and word n minus 1, or the last n words, the word n to word 1, or just the whole collection, right? Fast forward a few years from that language model approach, and bigram models and n-gram models were fairly common before LLM and BERT and so on. So what Google did with BERT was that now that you have all of those data that you can train from, can you pre-train a model to get a good representation of those data that can then be used as a common board, as an initial foundational model to then train other models with. So can you learn good representation of data? That was a biggest innovation in these pre-trained language models. And the implication was that once you have that pre-trained model, we only need few additional examples or small amount of additional task-specific label to train a task-specific model. So you have a pre-trained language model like BERT that can be trained unsupervised, that means without any human supervision or human labeling or human intervention, to train a language model that can then be trained on easy to obtain raw data. You use that as the base board for then fine-tuning a model on specific tasks, task A specific kind of data and labels. You have a supervised model now because you're going to give some sort of training saying, oh, now that you know what language is in medicine, if I give you these examples and this is the output I want you to give out to predict, can you learn it for this task? So that was the notion there. And then you can start with the same model and supervise it for a different task, fine tune the model for a different task, and then it'll do well on that task. So this was the kind of the basic kind of formulation for BERT or the transformer based models, right? Bidirectional encoding representations. Okay, so fast forward a few more years, you had this BERT, which is this bidirectional encoded representations from transformers, and then you had a new version, new avatar of that called generative pre-trained transformers. They both train on large data. They can be trained on specific data, but so BERT especially because it's a slightly smaller model, can be trained on different variants, and you can find slightly different models that come out of it. So BioBERT and PubMed BERT would be examples, or bioclinical BERT is an example that we have used that has been trained on clinical notes and clinical data. PubMed BERT has been trained on anything that's published in PubMed and other biomedical peer-reviewed literature. And then you train that on generic data, and then you fine tune on a task A, and it works pretty well on task A, right? And it has BERT models have started to give out kind of really state-of-the-art models that or state-of-the-art performance that traditional machine learning models were finding really hard to achieve. So it fundamentally changed that that ceiling that natural language processing models have. Generative pre-trained transformers are also models that are pre-trained on large corpora of generic data. But then with more and more parameters that you add to the model and you scale up those models, the key thing that happens is it works pretty well on many tasks all together and individually. That has been the significant change between BERT and GPT. And then with the variance of different amount of parameters, different number of parameters, started with GPT-2 and 3 and then 3.5, which is ChatGPT, and then 4, has made the model more and more and more powerful. So what makes these large language models different from other AI models? Well, recent work in natural language processing research, for example, have started kind of coalescing into this idea of emergent abilities for large language model. So an ability is considered emergent if it is not present in smaller models, but it starts showing up. It starts coming up when model sizes increases. This is very non-intuitive in traditional machine learning because traditional machine learning models have had the curse of large dimensionality. So they kind of say that, oh, with large models, things can get really complex. And so you want to narrow down the model, make the model smaller because you want to only keep key features, important features, so that the model doesn't get confused. But emergent ability is kind of the opposite. Takes that assumption out. So in this study that was published in 2022, it was tried out, this approach, this large language was tried out in a bunch of different techniques. Modular arithmetic is a numeric analysis approach. So let me use my slide here. Here you go. This one. Truthful QA is like a question answering system where you ask a question of the system and it gives you an answer, and then you test out how trustworthy those answers are. You can use it for multitask natural language understanding and other question answering and so on. And what you notice is, again and again, independent of the task, the models really perform at random, which is this dotted line, until the parameter space kind of becomes large enough, and then suddenly it performs really well. So what was really poor model until the model space of 10 raised to 22 suddenly becomes a model that performs at 30-40% accuracy. The same thing here with truthful QA or natural language understanding, where something that was only about 25% model accuracy increases to 60-70%. So this notion of suddenly giving a large model makes the model do things it could not do when the model was smaller. I'll say slightly smaller, but not really slightly, right? It's order of magnitude higher, but still, when models were smaller, is unique to LLMs. So what are examples of these emergent abilities? First one was the in-context learning. And you'll see as I'm kind of describing them that these are how large language models are being used now that we have those APIs that people can play with, right? So first example is you give instruction to the model, you give some examples to the model, and then you give a test input and say, can you do the task that I have just told you about, giving you instructions for and giving you 2 examples for on this task. So an example of that from a non-medical domain, let's say, is translating English to French. It is not necessarily that out of the realm, by the way, because in a lot of work that medical NLP researchers have worked on, they have almost considered medical language as a slightly different language than English. And you're trying to simplify the language to English, right? An example of that would be prescription directions. If you use something like one tab, POQID, which is the Latin phrasing of take this 1 tablet by mouth 4 times a day, has to be translated to that English to really to understand that instruction. So this translation task does not have to be from 2 very different languages. It's very well live and present in medical data also. So if you have to translate English to French, and you give examples, you give an English example and you give a French example, and then you give another English example and a French example, and then just give the English test. It is supposed to then find out what that is. Importantly, what you have not told the model, so how it has been different from previous models is that earlier you would tell this mapping, this alignment between a second language and the first language. So in machine translation research, what people have done is, malaise maps to discomfort. That mapping is something that machine should know because then it can learn from it. Or this word language is matched to language, or formatage matches to formatting, right? So there is some sort of an alignment between these two. Or in medical domain, PO stands for by mouth. So you're kind of giving that information as something that the machine should know. But here, you have not said that. You have just given examples. You have said, okay, for this example, this is the output. Figure out why that mapping works and then learn from it. So when you do this task where you only give the instruction and the test input and expect the model to learn it to do the task, that is called a zero-shot model. When you give examples, that's called few-shot model, and then that few shots of those few examples. And sometimes you give only the examples and the test, not give the instruction, and then that will be a few-shot model without instruction. So you're just giving, so it's learning by example. You say, I don't know what the task is, or I'm not going to tell you what the task is. It doesn't really matter because I don't need to tell you. Look at this example and figure out the task, and then do that task for this input test. Okay. So with that, so that's example number 1. Example number two is a chain of thought prompting, which again now with prompt engineering you would have heard of, seen, done, and that is um, the comparison between kind of what a standard prompting should be. So prompting is this instruction, right? So how can you give the instruction in a much cleaner way? It's known, it's still true that these models, large language models and GPT models, don't necessarily work very well with numbers, with playing with numbers, doing computation with numbers. It is improving. It will get better. But even a couple of days back, there was a context in which I was kind of, or somebody close to me was putting in a number because they trusted LLMs, ChatGPT, much more than actually doing the math themselves, and they didn't give the right answer. In the original case, you have something like you just ask the question, give the answer, then ask another question, and then it's supposed to give the answer. But in the chain of thought prompting, you are basically giving the answer in terms of these are the logical steps, or these are the typical steps you would do to get to the answer. So where you kind of said, okay, you are working out the problem there, and then giving the answer, and that way then by asking the model to work out the problem, in this case, it did the right thing and gave the right answer. But this idea of chain of thought prompting is leading towards explainable AI models, or to models that at least can justify the reasoning for which it has done the label or the output the way it has, so that humans can evaluate it, so that we can check that it is getting the right answer for the right reasons, and not necessarily just generating the answer out of thin air, right? So that would be one kind of important one to as a chain of thought example. Again, an emergent example that was very difficult to do earlier, because you have to then probe the model to find out which features work, or which layers of the model worked well to give the answer. But now you are kind of asking it to generate reasons. Now that opens up another kind of worms of really evaluating the reasons itself, but at least that's in the right direction to build trust on these models. So why do LLMs have these emergent abilities? Why is it that a typical language model, or even earlier versions of these large language models, were not able to do these things, and they are able to be done now with these larger models? We don't know. That is a kind of still an area of research. There are a lot of hypotheses about why that is the case, but it is still not settled science to know really why. And that is kind of important to realize, that as of now, people are using it because it does the job the way they have evaluated it, but not really understood why. Jan, I'm going to come to you for your question in a minute. Let me just finish this thought and come back. So the possible hypotheses there are that one, that you have learned this representation of these data. So you are actually training on all of this large corpus, not just on these few examples that you're giving. The model with these many kind of parameters has the capacity to remember much larger patterns, and much kind of complex patterns that can be derived from these large data it is training on, it's pre-training on. The fact that there are orders of magnitude more parameters makes it kind of closer and closer to really ability to kind of learn differently, where not all solutions are going to get to the answer and will get lost, but there is hidden information in these hidden layers that you can pull from when the task needs it to, right? It's more complex because they are neural network models compared to simple linear models, or even exponential transformations of linear models. And these multiple layers are kind of creating that space by which you can learn all of these parameters. Some question whether it is in the instruction tuning, because you kind of give them an instruction. The first time you give the instruction, it never works. You're going to tune the instruction to see which is a better way of getting the same answer. But then you are prompting the machine multiple times to kind of give you the answer that you are expecting it to give. And that itself is teaching the model something. And some kind of indicate the reinforcement learning using human feedback as the reason for it, where you are not only doing instruction tuning, but you're also giving examples of what worked and what didn't work, and then that way the model is reinforcing what it got right based on the human feedback that's coming in. So that is really where the continuous learning loop comes up, because you are continuously training the model and making the model better, not only for the task that you are trying to teach the model, but you're also teaching it general information so that it can use it for other tasks as well. And finally, whether it's because it is doing all of them together. There were evidence of multitask learning doing better than individual tasks even earlier, even pre large language model era. But with these additional parameters and the fact that finding the next word itself is inherently multitasking exercise probably helps. For example, when you're looking at a paragraph that is auto-generated, and look at how the next word comes up, the fact that Johns is followed by Hopkins, or Maryland, Baltimore is followed by Maryland, gives you information that there's a lot of information that you need to know. The name, the geography kind of information or world knowledge, some sort of anaphora resolution where you're talking about Johns Hopkins, and the correct pronoun to use in this case would be he rather than anything else. Things like that become important. Okay, I'm going to take a little bit of break because this is actually, before I come to this next point, there was a question. So I'm going to take that question now. Okay, so the question that was asked, at least in the question answering session, was, so how did a model get 27 as the answer? So we'll go and talk about that in a minute. JJ, I know, had a hand raised, but I don't see a question from them. But let me answer Valeria's question until then. Okay, so the question was, how did the model get the answer 27 for this last one? You can think of some combination of these numbers that so it's really learning from the first exercise, right? So from the first example of getting to 11, that uses the numbers 5, 2, and 3, and then trying to do something similar with 27. So in when I was kind of thinking about it, it was something like, so now this was my logic when I got it. It is doing the third number plus 1 time what did I do there? It was 5 plus 6. There is a you can write down mathematical equation with 3 variables, x, y, and z, and fill up 5, 2, and 3 and get 11, and put 23, 20, and 6 and get 27. So that was what my kind of logic was when I did it. Now I'm not getting it right now, but if you figure out, you can find multiple kind of variations of those numbers that will give you that combination that will give you this answer. But even if that was not the case, so let me expand on your question and kind of go beyond that. Why would it give out number 27? It could be pulling it from thin air, right? Or for all practical purposes, still doing something like that. It knows that what needs to be filled there is a number, and it is doing something to kind of fill that number, because it is, after all, a generative task. So it's not going to give you the answer. The answer is beautiful, right? It knows that it's a number as an output. It also probably knows that in the space of these numbers, you're not going to give a 2 million or a 1 by 5,000 or as a number. But that is not enough. That is why this chain of thought prompting of really getting to the answer is probably going to be helpful. We have had another example where we asked the large language model to pull out data from a table. We gave it a table. This is a work in collaboration with Diana Merritt-Isserman, who is in School of Nursing and really leading the work. Even though I'm collaborating with her, she's the one leading the work with students. Where we had a peer-reviewed literature example where we gave it a table and said, can you recreate this table in an Excel sheet or something? Like basically get a computable version of this PDF image of a table. You would notice that it would do very well on a lot of cells. So it would be able to identify the lines, the columns, the numbers within those cells, and pull those out. And then randomly, for no real reason or apparent reason, change those numbers or reorder those numbers. Or when you have an empty cell here, it doesn't know how to handle empty cell, and it's going to push everything else after that by a cell because it's trying to fill every cell. So it made mistakes. It made lots of mistakes. The problem is humans make those mistakes too. So comparison to human evaluation, it was slightly worse, but not terrible. But you expect the machines to do very, very well, especially if it knows to do 90% of the task well. So the challenge then becomes, how do we know that the machine has gotten it right or wrong? That was something that if you give it an easy table, it does a very good job of identifying all the cells. You feel it is confident that it knows structure, it knows the physical space of a table where you have rows and columns and table and column headers and row headers and so on, for it to kind of pull it out, but still it makes mistakes fairly at random, and we don't know why that it made that mistake. So your question kind of reminded me of that one where you try to argue, you try to, even I did it, right? With this example of why it's 27, try to come up with this, oh, this is probably the model it created, but it may not have done that. It may have just kind of generated text as what it is supposed to be doing, generating numbers. Is that's the aspect it's supposed to do. Hopefully I answered your question. Let me have one more question, I think. So why did the evaluation metrics without ground, how did the evaluation metrics without ground truth evolve? Excellent question. If you give me Yichin, if hopefully I pronounce your name right, give me one more slide. I want to kind of talk about it and get to your question, because but your question was really a good segue into what I was going to talk about next. Okay, so why? So now that we are working with large language models, how do we work with it in a scientific way, in a true as a true scientist? What has happened pre-LLMs through rigorous research is a workflow like this. We generate an idea, or we think of a task that for which we have a possible solution. We think carefully whether this idea matches our intuitions for the language or for learning or for the task at hand. If it doesn't match the intuition, we say probably it's not the right approach, and we go back and try another idea. If we feel that the intuition matches, then we implement that idea, we experiment it, we show that that idea actually works, we revise it, improve it, tune it with another additional idea, right? So we decide on a model being good or bad, not only based on whether the model does it a good job, but whether it does a good job for the right reason, whether we can explain the output, whether it matches our intuitions. However, more and more examples now are coming up with this aha research idea. And that is, you are generating an idea or have a task at hand, and you assume that LLM can handle it, whatever that task is, and you implement it or let LLM do that task and then revise by doing instruction tuning or other kind of tuning, right? But you are assuming that the large language models can handle that task. You are giving instructions like, assume you are a clinical psychologist, and then give the instruction after that. The machine doesn't know what a clinical psychologist does or is supposed to be doing, unless it has seen that in examples in data about really what the scope of work is. By using those words, one tends to feel that, oh, that is probably the mistake. I didn't give the example of you are a clinical psychologist or you are a clinical psychologist who works in alcohol clinic. I need to do that kind of tuning because that is the reason why LLM did not do well. But that may not be the reason at all. You are relying, you as in not each of you individually, we are relying on large language models to be able to do a task that we have not defined well ourselves. Please don't do it. Please go back to the tested methodology of machine learning research. That is the key thing. So one of the specific examples that I keep giving to my students, but also others, and I'm going to give today, is evaluate large language models on a task that you already know how to evaluate well, that you have enough training data and evaluation data on, and do not change the task for the benefit of LLM. Let the model actually do the task that you were trying to learn a support vector machine or logistic regression or any other kind of model to do, and evaluate it then. It might still do well, but at least you are comparing apples to apples. What happens now is this aha research idea, and that is that you change or you tweak the task, saying, oh, but machines are generative models, right? Large language models. So let's kind of generate text and see whether the text that it generates makes sense. Obviously, it's going to make sense because that is what it is trained on. It is trained on a large language model to see and give out coherent text. Coherence is not going to be an issue. It is factuality that's going to be an issue. And that has to be against data set that we know very well of. So to answer each in your question, why did it happen that we have suddenly started developing approaches where evaluation is and ground truth is not important anymore, is wrong. And the fact that you are pointing that out is absolutely valid. It's a great observation, and I'm cautioning folks to not do more and more research that way, because it doesn't serve the purpose. It's all going to be this aha effect that might die out. But large language models are indeed really powerful, that you can learn a lot more about them if they are systematically studied and evaluated on. It will take time. That is the problem, and that is our biggest kind of enemy, I think, here. It'll take time because it needs those intuitions to be borne out in the data that we see. Hopefully, I answered your question. Okay, so in this first phase, and kind of closing that one, let me kind of finish with this idea. Figuring out when AI makes errors is important. It is important for the future development of these AI models and applications of these AI models. So why did the model make the decision it made? That gives rise to additional research, area of research called contextual explanations and explainable AI. How can these errors be corrected? That leads to this notion of additional training, fine tuning, instruction tuning, prompt engineering, RAG, right? So retrieval augmented generation. All of those are in that bucket, because you have figured out, you have seen that it is doing a mistake, and then you're trying to fix that error, correct that error. How can human input improve AI models? That is this line of reinforcement learning using human feedback, or providing the right kind of human feedback, where a lot of research in machine learning on active learning and kind of oracle learning and so on has a place in doing it for large language models too. Okay, so a final thought. This notion of responsible AI is something that a few students in my research group are working on. I'm not going to pull out them and call them out, as I'm going to do in the second half of my talk with other two other case studies, but specifically kind of reliability of the model, fairness of the model, accountability. That means are we doing it against rigorous evaluation criteria? Are we protecting the privacy of training data, or can the models be attacked based on changes to training data or model evaluation? Are all absolutely valid kind of areas of research. One of my students finished his dissertation on attacks and defense on these large models. Another student is kind of actively working on this privacy preservation of training data. So it's really absolutely active area of research right now. Okay, so let's take a little bit of break. We kind of covered first part of it in the first hour, and I promise we are going to finish the other two in less than an hour's time. But let's take about a 5-minute break. Gives me some time to kind of drink water and reset. But if you want to take a bio break, that's a good time also. But please do have your questions flowing. I'll collect all of them and start with the questions when we come back. Let's take 5 minutes break. We'll meet at 10:07 Eastern time. Thank you. Okay, welcome back. Um, can I had muted it and kind of unmuted my microphone, so I just want to make sure people are here able to hear me. You can raise your hand. Thank you. Thank you so much, Wisdom. Thank you. Okay, great. So, in the first hour, we kind of really set the ground foundation on large language models. And I kind of highlighted really the emergent ability of models. And now instead of when I was kind of putting this together, I was thinking of whether to kind of go with math behind it and really kind of understanding these models in more detail through their kind of how exactly these models are evolving or what they are doing, or really talk about applications in health, which is kind of the area of focus for our MIDAS series this term. And through examples, kind of show how practically you could use these large language models for the task. What would be kind of tasks that what was happening when we were not using the task, and then what was happening when we're not using these large language models, and then when we add them, what happens? How does it improve? So that is the flavor of the second part. We are starting at it's close to 10:10 now, but I promise you I'll kind of finish these in around 30-40 minutes. So we give enough time after for questions. But please do have your questions flowing if you have them right now. Okay. So the second part of the talk is really going to be a use case on risky alcohol use. I introduced that a little bit, but I'm going to be more formally introducing it now. This work is in close collaboration with Anne Fernandez, who is in psychiatry, our Department of Psychiatry. She and I have a grant from NIAAA on this task, and most of the kind of results that we hear are really coming out of that funded effort. And really the effort that supported Kate Weber, who is here in the second photo, and a lot of slides are from her dissertation. She graduated recently, so super happy for her, but also that this work kind of really highlights the work that she has done in her dissertation research. Okay, so what is this problem of identifying risky alcohol use from EHRs, and why is it a dissertation level of work, right? Um, so uh, there are guidelines clearly on what is considered drinking too much. As I kind of highlighted, it is 15 or more drinks for men, 8 or more drinks for women, but it's also this notion of binge drinking, 5 or more drinks in one occasion for men, and 4 or more drinks in one occasion for women. The drink itself is standardized. You have these standard drink measures, and it's fairly understood in clinical care that when they are talking about drinks, and as we saw in the documentation, this person drinks for 2 drinks a night or something like that. They are using the standard drink measure, where the conversion from actual alcoholic content to the units is already done, right? But for people, you should realize. I mean, it's important to know that it's not one quantity. It's not the same quantity. It's not an ounce of beer and an ounce of wine mean the same. They are not, right? Because of the alcoholic. Okay. That said, sorry, wrong one. The the reason to identify risky alcohol use behaviors is that it is associated with poor surgical outcomes. So if you have if a patient has risky alcohol use behavior pre-surgery, there are complications post-surgery, more time to recover, possibly higher probabilities of opioid overuse, and so on. So there are and actual complications themselves in terms of delayed kind of getting better, taking longer time to get better. Um, the existing screening that happens for identifying risk alcohol use in a pre-surgical setting is limited, so we wanted some intervention. And the key problem is this risky alcohol use is inconsistently documented in electronic health records structured data. What is documented is alcohol dependence, which is this final stage where there are real implications for health in terms of alcohol kind of related disorders that then get coded because they have ICD codes associated with them. But we want to kind of identify them, not only those who are at that advanced stage, but really those who have high risk of alcohol use. So we came up with this kind of definition. Really, Anne is the mastermind or brainchild or whatever you want to call it of alcohol research. So she's the one kind of who led this work. Where you define these four classes: no alcohol, low risk alcohol use, high risk alcohol use, and probable alcohol dependence, in terms of these different factors that go into them. So if there is no evidence of drinking the alcohol for a sustained period of time, then it is the yellow one here. If there is no evidence of heavy drinking, but or intoxication or any alcohol-related consequence, then that will be considered low risk. In general, the default is low risk, right? It is much more common to be drinking, but under limits than not drinking at all. High risk alcohol use is when you have some diagnostic codes of alcohol abuse or alcohol overuse, or heavy evidence of heavy drinking. And probable alcohol dependence has not only those, but also evidence of treatment of alcohol use or alcohol withdrawal or prescriptions for alcohol use disorder medications and so on. And then there is this notion, the gray box of no mention, which is a class of itself because you just do not have any information in the notes. So notes would not be able to give you any evidence one way or the other. You can default it and put it into low risk, but that is different from actually somebody who has evidence of low risk of alcohol use. Okay, so that is kind of the description. Nothing else in the text. So big kind of result is when we only look at a two-class model, whether they are they have diagnostic kind of evidence of alcohol use or not, we find that even if we use that and we have administrative data on ICD codes, the number of true examples we find are a third of what you could find if you use NLP. So there is documentation in free text that tell about this person's heavy alcohol use, but that does not translate into an ICD code that gets recorded, and that's what is searched for when we are searching for any of these cohort identification tasks. So my first takeaway that for all of you is looking at just the code, which is how a majority of health service researches happen. You are missing out patients who are not diagnosed, who are either underdiagnosed or misdiagnosed for the condition that you have. And time again, we have seen that example happen. We have done that for at least three other clinical phenotypes that I can point out where that is also true. Okay, so that was just the simple, straightforward kind of model. The traditional approach for this binary model follows our typical pipeline. I'm not necessarily going to go through it in a lot of detail, but this is something that you would have seen. It is primarily rule-based or machine-based kind of machine learning-based models where you take a patient record. It's still important for you to know what happens in an NLP. So that's why I had this slide here. You could use the structured data, which means anything that comes out in a database, to identify, let's say, the ICD diagnostic codes, and use those decision rules to get a structured data only model, which was that 29% model, right? But then if you look at unstructured data, you can take a patient record, you can segment them into relevant sections like patient history, family history, social history, and so on. Identify the hotspots. Where does the information about drinking come in? It's in social history. It's not going to be in assessment and plan, for example, right? And then you identify negation, you identify templated text and remove the text. So for example, a good templated text that comes again and again is whenever patients are given instructions before surgery, let's say, you would have a standard instruction like, do not drink alcohol before surgery. That fact that you have an instruction saying do not drink alcohol does not mean that the patient drinks alcohol, right? It is just a standard templated text that is added. So if only occurrence of alcohol in a note is in instructions like these, that would probably mean that the person actually does not drink alcohol at all. Right? So that is an example of a templated text, but there are other templated texts also the same way. You have to kind of identify the patient's sex because this particular task is a task space that needs that as an input. It is a different decision depending on the patient's sex, and we are using biological sex in this case. And then you do numeric analysis where you convert the numbers into, let's say, if it is 2 drinks a night, you have to convert it to 14 drinks a week, right? So that kind of numeric analysis. Then you have some information about family history and patient history, and especially mentions of alcohol, whether it is under family history or patient history. And then doing a segment level classification, and then boiling it up to patient level classification. So typical natural language processing pipeline, whenever we are kind of running standard NLP pipelines, we are running this pipeline in some form, right? The performance of this, the numbers, as I said, about 29 and 87 are coming from here. So if I kind of show you, here. So 29 sensitivity of 0.29 and the sensitivity of 0.87, that was the two positive examples that we highlighted earlier. But in general, even with that, if you include specificity or positive predictive value, again, positive predictive value is better for the NLP model as compared to ICD codes. Specificity is slightly better for the ICD codes, but you see that it's missing so many that just by itself, that is not useful information. F1 is an harmonic mean of positive predictive value and sensitivity, and clearly, F1 is better for the natural language processing model. Okay, but if you go from this 2-class model to a 4-class model, which is what we defined, the no risk, or low risk, high risk, and then alcohol dependence, you see that they are not equally distributed in our patient population. They are widely imbalanced data sets, and so about 60% of them are low risk. And there are different rules for different sexes, right? But the contextual clues are everywhere in the notes. So if this is a kind of a very small snippet of text, you will notice that there is information about alcohol content, kind of drinking alcohol, so administered drinking for alcoholic beverages, so usually hard liquor daily. That shows that this person drinks at a high level. But the last drink was in July of 2013, so he has been sober for some time. So you have both those information. And then you have, even with that, the person has end-stage liver disease. So now if you see that they don't drink right now, and they have not been drinking for 10 years, but because they have had so much drink early in their life, and they have end-stage liver disease now, which is an alcohol-dependent modifier, the true label here would still be probable dependence, right? Even if they are sober for some time. Okay, so that is how you kind of infer a label for this task, right? How would we go about doing it? So this was a long-running kind of project. So when we started, LLMs were kind of a slightly early stages. So we kind of worked with our machine learning models, and we had rule-based approaches and expert machine learning models doing this pre-processing and rule-based inferencing. I'm not going to too much detail in that, but there is logic behind it. That was the kind of main purpose of this slide. And what we find it for that for a 4-class model, the F1 measure, higher numbers are better again, is just 0.45. Okay, so rule-based don't work well. We are not super surprised. It happens. This is a skewed distribution, so it's not uncommon to see numbers in a 4-class skewed distribution to be around this value. It's not a terrible model. It's just not good enough. Then we kind of use, let's say, whether use machine learning approaches and try to build that. The performance doesn't increase much. So that's a surprise, but that happens too. So rule-based models are still kind of in the ballpark same way, 0.43. Cannot be used for real tasks, right? For applying it in health data. So then the question becomes, where is the model underperforming? Understanding that is the key. So what we noticed here is for so again, this is split on sex. So you have pink circles are female, orange circles are female, green circles are male. You'll see that for low risk, which is the 60% of our data set, the information is really up there. So very high precision, very high recall. No alcohol is also pretty good. When it is high risk and alcohol dependence, the performance is low. Now, those two are rare classes also. They are not as many people, but we do not do a good job on recall overall, at least in these models, right? But the problem is, especially here in probability dependence, you'll see that the female identification is really, really low, close to zero. So even though it does somewhat better on male patients, it does really terribly on female patients. That happens in other ones too, to some degree, but that is a cause of concern. That happens in high risk here as well, right? Okay, so the core issues here are there are underlying thresholds for men and women. They are different. So we know that going in. So it has to be a model that is separate for different decision making depending on the sex of the patient. So it's not that kind of a bias, right? But there's a data bias. So there are very few examples of high risk or dependent women. So learning from them in a data set is really poor. And then in general, a tiny proportion of the data set contains examples of the information that you are most interested in. The two most important classes of high risk and alcohol dependence, probability dependence, are rare classes. So there is that skew. But there's also a skew about data itself. The amount of data that is in an electronic health record is huge for the little tiny bit of information you want to know about probability dependence or alcohol related information. So that is a tiny proportion that we are really talking about here. So how do we then improve this model? We utilize a salient kind of treasure trove that was ignored earlier. And that is, we had asked human annotators to go in and identify the true label for each of these patients, these 1,000 patients, but also to tell why they thought that was the reason. So there was these annotations about really their reasoning is just highlighted text from the clinical notes to kind of say this is the reason why they believed that they are right in the label that they are giving. So what we have is not 1,000 labeled examples for these 4 classes, but about 8,400 note sections that have been annotated with reasons for this risky alcohol use label. So that information can be used to concentrate this information on a stage-by-stage basis using a robust NLP pipeline. We started with the same kind of approaches using rule-based and machine learning-based approaches, but then we added what we're calling the auto annotator. We used a deep learning-based model and a transformer-based model to do auto annotation of the data, training that model for the task that's at hand, that is identifying these different factors from the notes, and then run a bidirectional STM model at the end, which is again a deep learning based model as the final classifier for a patient level inference. So the steps there are, yes, we are doing text cleaning and entity detection early on. We are reducing the amount that needs to be processed. We are reducing false positives. But then when you come to the big innovative component, which is the auto annotator, we are leveraging these labeled data, maximizing the training on those labeled data by identifying the sections that are most important and concentrating that information just for those sections, and in a way generating features. I don't want to call it, I said generating features and putting air quotes around it because deep learning models, you don't typically generate features, right? You are giving it a setup that is able to kind of only focus on the sections that are of importance and ignore sections that are not important. So that is how you're concentrating knowledge or information from the data that is training on, and then kind of using a deep learning model to infer the label. Okay, so long story short, the overall accuracy then, what was 0.45, increased to 0.87 with a weighted F1 of 0.91, which was significantly better than even the rule-based model, which is what we wanted eventually to achieve. And it is this approach of using the large language models exactly where it works well. So this is BERT model, exactly where it works well to improve the model. So the key takeaways are, yes, large language models are promising, powerful technology. They need to be carefully deployed, though, in supporting this human decision-making task. The unstructured component of this free text data is rich with contextual clues that can be used in a well-crafted AI model. And natural language processing pipelines are not just one solution. They are not just large language models. It is a pipeline that goes from rule-based approaches to deep learning and transformers and generative AI models. It would be wrong to only focus on one kind of model and especially in a task where evaluation is hard. So asking the right questions and then building the models is important. Okay. The so this is a good break for any subsequent questions if there are. And I'll take a sip of water before we move on to the third task. Sorry, third section. Okay. If not, let's move on and then we'll leave enough time for questions later on. Oh, there is a question. Okay. Let me just quickly check this one. Okay. So the question is from Yuchun again. Does the bidirectional LSTM labeler only read the number of occurrences of keywords annotated? Okay. Um, so the question is the last stage here of bidirectional LSTM labeler. What is it? What is it seeing? What is it training on? What is it making its decision on? So it is actually looking at the a weight distribution. So what it is getting is like a vector of different. Now I'm calling it features, okay, but you can think of it as a 30-dimensional representation of the trained models where different factors like is the information about alcohol use present in this section of the node or some other kind of again features is for the lack of other words I'm saying features. So it's a 30-dimensional representation of these data that goes in as input into the bidirectional STM model. So think of it as instead of an input representation that is on a one-hot representation of the original text, that is what is input to auto annotator. The output of auto annotator is a condensed or a transformed representation of that one-hot representation, which is a manageable 30 to 50 dimensional representation. Okay. Hope that answers your question. Okay. There's one more question. So let's kind of handle that before moving to the next one. Can LLMs be trained using survey data to predict health behaviors as we do with predictive machine learning models? Yes. So I'm trying to think whether. Okay, let me answer it right now. I'll answer in a short way, but if there is more time at the end of the talk, I'll give you more examples. Absolutely. So in a recent work, what we're going to look at is if you have survey data, the kind of analysis that happens for qualitative data for basically qualitative data analysis is coding, right? Coding the themes that are being discussed, coding the aspects of, and this is not programming coding. This is like the qualitative coding of them. So we had a kind of models that where we have tried using natural language processing to assist with coding. It's not, I'm not going to call it automated coding. You still need human, especially qualitative researchers, to involve and direct what kind of coding makes sense for the task that they have at hand. What is the application they're going to use it for, and then come up with those themes, and then let the machine do what it does best, which is identifying themes within the patterns, finding out what responses are most closely affiliated with that theme at hand, generate some sort of a summary of that theme, and so on. Okay, so I'm more than happy to kind of talk to you about it. We have two projects that I can kind of specifically point to, but because you are an anonymous attorney, I don't know who you are, but please reach out to me over email. Thank you. Okay. Couple more questions I might defer to later. Okay, thank you. Okay, because you kind of answered it. That's perfect. Thank you. Okay, great. So with that, let's kind of move to the third part, and this would be even shorter if you can assume, if you can believe me. This work is an ongoing work that Pei Han is doing in my research group. She's a graduate student close to graduating over this academic year, working on Alzheimer's disease and related dementias. And the main kind of case that she's kind of working on is the fact that Alzheimer's disease and Alzheimer's disease related dementias are very prevalent. but still underdiagnosed and misdiagnosed. So we have seen this problem for the other one also, right? So that happens here too. This notion of underdiagnosis. But related dementias include Lewy body dementia, frontotemporal dementia, vascular cognitive impairment in dementia, and multiple etiology dementias. And so our goal for the study is to focus on identifying dementia patients based on their electronic health records. So again, a computable phenotyping task that where you need to identify cognitive impairment because again, it's useful in downstream tasks and to facilitate pragmatic trials related to people living with dementia. So dementia, yes, it is underdiagnosed and misdiagnosed. So again, the ICD codes don't do well, but they don't do well for multiple other reasons. And that is my definition of Alzheimer's disease can be slightly different than your definition of Alzheimer's disease. And so when we discuss how many patients we have in our institution, we are not comparing apples to apples. So there is that problem also. But more fundamentally, the issue is there are a lot of dementia phenotypes. So when you're talking about characteristics, it is not one label at the end, as it was with alcohol use, right? There's one definition. Here you have a bunch of them, 25 different factors that go into what would be a dementia model. For example, whether they are able to do activities of daily living. Are they able to do their tasks independently? Are they able to kind of manage finances? Are they able to drive and transport themselves and so on? There are memory issues. Are they able to recollect facts? There is executive function where they are able to make decisions, or speech, and whether they have difficulty finding words, visuotemporal, and so on. So there's a bunch of different things that go into determining whether a patient is at what stage of dementia. So our initial round of kind of cognitive phenotyping was to create a label data set, very much similar idea as before, where we are looking at different kinds of notes coming from family medicine, primary care, sorry for the typo there, and general internal medicine, and also consult notes and progress notes, and then discharge summaries, and then have initial round of annotations of really identifying these characteristics in patients living with dementia or mild cognitive impairment. And a third, LD control. Then we develop a BERT-based named entity recognition auto annotation model. So we created a BERT-based labeler, very much like an auto annotator, right? To facilitate this annotation that was then evaluated or validated by two additional annotators. So we used the LLM model not to learn a better model as it was in the case one, but here to generate the labels that can be given back to our annotators, our human annotators, to check whether they got the annotation right or wrong. So that way, then you have a continuous feedback for the annotator itself, but the task of actually labeling is significantly easier for the annotators. So that way, then we were able to annotate even many more, like 500 more new patients. Okay, a quick kind of word on the auto annotation model. We are again using BERT, which is a multi-layer bidirectional transformer encoder model. We pre-train it on the different domains of kind of medical data. So bioclinical BERT is an example, and it has been used successfully for a lot of downstream tasks because it kind of learns this contextual word embedding well. So once we have that kind of model with BERT, we are using it as an annotation aid, where BERT is used as an entity extractor. So we are the kind of question we are asking is almost like a question answering system. What is the symptom or function or medication or screening or test score that is mentioned in this text, right? So you are kind of asking it an open-ended question, not really saying find this particular thing, but what is the thing mentioned, and the model is trained to identify spans of text that tell you whether that particular entity, like a function or a symptom, is present in this text, and if so, then where is it in the text? So it is an extraction setup, but the kind of the way the model is getting trained or asked is using a machine reading comprehension, like a question answering task. Okay. Again, going directly to results and not into details of the model, we had first tried a long former model, which is this long document transformer model with multiple attention layers that can help process these long documents. Electronic health records are long documents. Um, it was not the model we used for the previous task because we were dividing the document into subsections, small sections, and then only sending small sections, right? Here, we don't know where that information could come from, so we have to kind of really send the whole document. So again, task-specific changes to the model. And then we kind of use specifically the clinical long former model that is pre-trained on clinical data. Our first view of the results appears that all the things it's doing really, really well. Almost all of the factors that we have there, it is more than 90% accurate. Gate, which is the last column here, is the only one that is below 90, but is still above 80, right? So it looks excellent. This is an excellent model. But if you look at it closely, it is also prone to significant changes in the distribution. There are many examples where there are hardly any instances, and it doesn't. They are rare classes. They are very few, so they don't add up to the final accuracy score. But the distribution of performance is really skewed. Really, only four of them have a recall of even greater than 0.5. About 8 or 9 have greater than 0.5 for precision. So not a good model, right? So this is the why you need to see and evaluate the model for the task at hand to actually see whether the model does well or not. So the approach that we use then for this is really multiple stages and a hybrid model. So we have a multi-label long former model that we just talked about that will be used for these common, very prevalent examples where it does well: memory, mood, neurodegenerative disorders. But then we have a section that first enhances the recall using pattern-based approaches that appears to work well for the activities of daily living because you can zoom in because the words are so fairly used so commonly that you can zoom into the context. You don't have to be the whole context like what you do for long former model. You can narrow down the context and just give a sentence or a paragraph, and it does very well once that has been narrowed down for it. Using for all of these kind of additional activities of daily living. And then and also for the miscellaneous task of motor, sleep, and speech. And if it doesn't go through that, if it still doesn't do well, then we are using a precision enhancer that is using based on a few shot learning, a different LLM model. So that's the Llama model, right? And that is used for really rare classes or that needs a lot of context. That is not specific to a single sentence context. Where aberrant and educated behavior, for example, or orientation in speech and language are examples of that. So this Llama 3 model is a powerful kind of large language model. It is trained on models of sequences as long as 8,000 tokens. It can be deployed locally, so it handles PHI well. We have used the Llama 3 8 billion parameter model, but as shown in the right side here, the Llama 370 billion model is the one that is really, really powerful, the large model Llama 3, and has shown significantly kind of winning over Claude and Mistral and GPT 3.5 and so on. We use the 8 billion model because it is again running within an academic setting, but I think we will probably be trying the 70 billion model too, if possible, and also evaluated whether how many examples we should give: 2-shot model or 25-shot model that is randomly changed with the training data itself. But so active experimental design here, right? So that is the other kind of line of what the question previously asked about. We have to do multiple experiments to see whether our first idea is the best idea or not, or tune the parameters or validate the results based on parameter tuning. So this is what that is. Okay, so specifically on prompt tuning, we for activities of daily living, we had an instruction like this. I was making joke of that earlier, but we used it too. So you can see that whether that helps or not. But really looking at ADL phenotyping, yes or no, and then give some examples, or a very similar instruction for phenotype itself. So instead of ADL phenotype, to give the phenotype and say yes or no, and give examples. The difference here is you're giving kind of label on the left hand side for kind of really whether they need assistance or not, or on the right hand side whether it's an abnormal phenotype, right? And again, kind of big summary there is adding these prompt tuning kind of as compared to the other ones helps improve the performance, but by overall performance by as high as 8%. So that kind of helps the model even stronger. Okay, so the key conclusions with that is yes, there, we kind of created a comprehensive collection of these cognitive related phenotypes. Um, Understanding that ADRD detection is not a one label problem. It is actually have multiple different things you need to identify before you can make a determination of whether the patient is an Alzheimer's disease patient or an ADRD patient. Transformer models do work well, transformer model, for example, but only when the prevalence is more than 10%. So don't go by the first results you get. Uh, and then I'll propose this recall enhancer and precision enhancer kind of effectively identifies these less common cognitive phenotypes. And finally, we have kind of almost like a rule-based kind of way to merge them. If the phenotype is not identified by the recall enhancer, then the person does not have that. It's a minimum risk of the patient having that particular phenotype. If it is identified by recall enhancer, but it's not identified by the precision enhancer, then it's a moderate risk. Maybe it needs further testing. But if it is identified by both recall enhancer and precision enhancer, then there is a high risk of this person having that particular phenotype. So you can kind of triage the output of your model in that way, by which you're combining not only one or not basing it on one large language model, but two large language models and a rule-based model kind of all working hand in hand to kind of determine where the approaches that that particular model provides is helpful, right? Okay, so to conclude, thank you for your rapt attention for the last 1 hour and 45 minutes. We talked about really three areas here, large language models and then two use cases. Large language models are here to stay, right? They are powerful models that have emergent abilities, but handle them with care. Do not use them as what has been called democratization of language models. I am completely in favor of people using it, but please use them with caution. Do not circumvent your study design because of this new technology. Learning from free text medical data does require well-crafted AI models. It is not always the case that large language models on the first one you try is the best model. Sometimes those models can still be improved by looking at the whole spectrum of available tools and how they can augment the decision-making system. NLP pipelines span these rule-based approaches to deep learning, transformers, and generative AI models. Um, there are active kind of ongoing work, not only in my lab, but elsewhere in this area. So this is not the final word. There's very much active work that's going on. And things that are presented here might change in a few months too. Thank you for your time. And now open for questions. So there are a bunch of questions that I have come in already, so that's great. Okay, so Madsen asks, at what cohort size, order of magnitude, is using LLMs for assistance in coding unstructured data worth it? Okay, and asking because I work with rare conditions with patients populations of the order of 10 to 100. Yes, so uh, it used to be fairly easy to give a rule of thumb answer on how much training data is needed. But with advanced models like these that are pre-trained, the model is being trained on a lot more data than what we would have given otherwise anyways. And that is why these few short learning approaches, even with 2 to 5 examples, seem to build a model that is usable. I say all of this with a caveat that it depends on your application. If you are in a highly sensitive application where your accuracy needs to be a 99%, it needs more work beyond what large language models might provide, because you even want to do a test on whether large language models are the right approaches for this. If it is a model where you are able to back it up with a human intervention of sorts, right? It is not going to directly be used, but it is going to be an aid for a human decision making. You can relax that condition a little bit. You just need to understand kinds of places where it makes a mistake. That said, so the using it for coding unstructured data, especially I'm assuming that you're talking about qualitative analysis. We have worked with it's a human in a loop approach. So we did not have already qualitatively coded data fed into the model, but really ask for it depending on how the model is confused about and kind of using it in an active learning setup. That approach, we were only providing as low as kind of 50 examples, but for the task that we were working on, and it still performed really well to identify the task that it was identifying. So my main suggestion is please to reach out. We can kind of talk about your specific use case, but the fact that your population is 10 to 100 is not a deterrent to using large language models. Ramesh Kauzi asks a question on, so great work, thank you. What are the pros and cons of this pipeline versus using a model like Llama 3 for all the risk categories instead of multiple? Good. So your question is, why don't we split the task, which is instead of a 4-class model, 1045, maybe it was for cognitive phenotyping that you're talking about. So then I'll change my answer to that. Assuming that you're talking about Alzheimer's disease, pros and cons of using a model like Llama 3. So you notice that we did use Llama 3 for as a third stage, as a precision enhancer. The so we did try using the same model for all of them, and it underperforms a long former model or a rule-based kind of or a pattern-based model if you use it for all of them. So it now, so that's an active area of work. So that's kind of the last stage of Pageant's dissertation. But really kind of looking at why a Llama 3 model works well for this case, and is it the case that sequence of long former to recall enhancer to precision enhancer is the right sequence, or can that be changed? Is not done yet. So hopefully I'll get a chance to come back and talk in a different venue about that, or you can read the paper that Pageant is going to write based on her dissertation research. Ijin is asking, check the understanding on hybrid approach. We are using different models for different aspects, memory, language, etc. How to decide which approach to use for each aspect based on experimental results. So yes, so your question is, once we know, so it is, so in traditional machine learning, we used to call it decision lists. We could have different additional decision making or machine learning depending on what you have already decided on and what needs to be decided more, right? So you can kind of progressively build on that, because what you are seeing in the second or third stage is the first stage examples are already gone. So your confusion matrix is going to be very different than if you are just learning it on all of the data. So yes, so it's empirical at this point, where we're kind of using this hybrid approach, but we're kind of sequencing it to see what works and what doesn't work. But that doesn't mean that we are using a greedy approach, which means if a decision has been made in a stage 1, that is never looked back in a stage 2 or a stage 3. So when you notice at the end, we kind of said we are combining the results of a recall enhancer and precision enhancer in a rule-based fashion for now. So that any errors that got introduced in stage 2 can get fixed in a stage 3. Right? So that's basically all I have to say for that right now. Again, active area of work. So this is not the last one. Another question is, why using bioclinical BERT is the state of the model for this MRC setting? It is very much again, to give context, bioclinical BERT is a BERT model that is trained on clinical notes in addition to other medical data coming from kind of PubMed research and so on. So that's what the bio comes from, and the clinical is the clinical notes. So it is really from, I think, mimic data that is kind of added to this model. So it has not only a general capture of clinical terminology and research language, right, in PubMed research, but also clinical documentation patterns and things about where what information is kind of mentioned becomes part of it too. So that together, the fact that it is trained on a clinical notes is helpful for this task where it is again kind of running on clinical notes. So that's kind of our understanding right now. Is it the best model for MRC setting? No, people have been trying different kind of transformer-based models. BERT is not necessarily the best and or the only one. It is just that the combination of the training on clinical data and the fact that it is a transformer model, I think, was the one that tipped in for it in tipped that in favor of other models. Okay. Another kind of question from an anonymous attendee. In case of non-medical usage of large language models with unstructured data, will you recommend using similar phenotypes or cluster analysis for categorizing technical documentation based on technical terms, relevance, application, etc.? I'm from a battery industry and I'm looking for incorporating similar techniques to classify technical documents. Absolutely. So, so the question is really on whether we use some sort of this topic modeling, cluster analysis, or phenotyping to do it. You would not call it phenotype, right? In that case, but more generally, what you're referring to is thematic analysis. So this is the bridge between the clinical phenotyping I talked about and the qualitative coding that earlier questions were talking about. This is kind of in that spectrum, a point on theme identification, thematic analysis, where so one of my kind of students is working on identifying themes from kind of from biomedical literature, right? Where you are trying to identify what is this paper or this document really focusing on. If it's a plan, for example, then what is this plan focusing on? What are the different aspects of it, and how does it align with other documents that are in the same one? So, in a way of kind of categorizing these documents, that seems to be useful. One of the ideas that he is using there is called a seeded topic model. That starts with a seeded like an LDA, but it's not LDA anymore. It's called an embedded topic model. Key ETM is the name of it. Again, please reach out and I can point you to that work. But that looks at embedding these. So when you're learning a representation, you're learning an learning an embedding in that representation space, and then using that to identify clusters of themes and then assigning documents to or parts of the documents to those teams. Hopefully, I answered your question. Right. I'll give a minute or so for folks to type in their questions and take a little bit of sip of water. And I hope I answered all questions in sequence and didn't skip one. I know that Krista, you had a question, but then that got answered. So that was the only one I did call out. Okay, great. Okay, good question. So how do you reach out to me? Excellent question. I usually have my email in the first one here, but I'm going to add in right now. Here, from the title slide, my email is vgvinodv@umich.edu. Please do reach out over email. Please do not hesitate to reach out again if I don't respond the first time. It is not that I am not interested in your question. It just happens that there are a lot of questions, a lot of emails. But please do please do repeat your email if you don't get an answer in a quick amount of time. Thank you very much. I promise that I'll leave you before the top of the hour. It's 3 minutes more before the top of the hour. So thank you for your time and for your for participation. I really enjoyed it, and hopefully we'll interact with you even more later on. Thank you.